one-dimensional motion with constant acceleration. So far, we have learned displacement, we have learned about velocity, and we have learned about acceleration. Now we're going to put them together to see how we can describe the motion, that means the position, time, and velocity, taking a constant acceleration, and describe this motion at different times and different positions. What's the relationship between the velocity at a given time and position and the velocity at another time and position if we know the acceleration, or if the acceleration is uniform? So this is what we're going to do. We have the motion in one dimension. That means we can have positive or negative values to show direction along this line. We need to define an origin, right? And everything to the right of that origin is going to be positive, to the left is going to be negative. Okay, so if we start with what we just learned about acceleration, we know acceleration is rate of change of velocity with time. So delta V over delta T. Here I am, acceleration equals delta V over delta T. Delta V can be opened out as V final minus V initial divided by T final minus T initial, yeah, for delta T. T initial is just 0. We start our time at some initial instant, which is time 0. So this whole term goes to 0. So we don't need to write T final, we can just write T, which means T at a given final point. Okay, so I'm going to get rid of this subscript and just reduce all of this denominator down to T. And for the numerator, remember I said sometimes we write V initial, or we might write V at time 0, right? Because T is 0 at that initial time. And again, for V final, it could be any final position. So we're not writing the subscript F, we're just going to write V. So this V and this T correspond to the same point, the point in time at which this is the velocity, okay? So this is just a rewriting of this expression in this way. So now the acceleration A equals V minus V naught over divided by T. If we rearrange this, multiply both sides by T, we're going to get AT equals V minus V0, and the two T's here cancel out. Taking this negative V0 to the other side and rearranging, we're going to get V equals V0 plus AT. Yeah? So this is called a kinematic equation, an equation in one dimension. It tells us that if we know the initial velocity at a given time, which is T0, and we know the uniform acceleration A, then after a given time, say 5 seconds, we can know what the velocity is, right? So that's what we're now saying, two different positions, one initial position, one some other position that we call final. Remember, the final position doesn't have to be a position at which the object is stopped. It's just any position along that direction, okay, that we are considering. So it's a given time, and this is going to be the given velocity at that time. If we look at the graphs, remember we started with a position time graph, which is my lowest graph here. So this is my position, this is time, okay? And the orange line here gives us the exact position for each of these different times, okay? And we learned when we were doing velocity that if you draw a tangent line, which is what this green line is, at any instant, so at this initial instant, the slope of this tangent line is going to tell you the instantaneous velocity. That means this is going to tell me my initial velocity, V0, at time t equals 0. I can find that number, and I can plot it on a new graph, which is a velocity time graph. I know my time is 0, and at that time 0, my velocity has to be V0. And then I can take the next, let's say, 10 seconds away. I can find the tangent slope of the tangent line here, and let's call that V10. I can find that number and go back up here at time t equals 10 seconds. I can plot that V10 and so on. So I get a whole set of points, which are all the slopes of instantaneous slopes at each of these different points. Here's another point, just some random point. Let's call this our final point. This has a slope V at a time t, and this is going to be plotted here. That value of V is at this point corresponding to this time. If you now join up all those dots that you just got from these slopes, you're going to get this straight line here, okay? does not always have to be a straight line. In this case, it happens to be a straight line. What does that tell us? That tells us that the velocity is increasing with time. Okay, it's a positive slope, so my object must be moving to the right with an increasing velocity. Yeah. And not only that, but the velocity is increasing at a constant rate. So because this line has just one fixed slope, which is rise over run. So if I choose 2 points, this is my rise, this is my run. The run is delta t, and the rise is a change in velocity, delta v. Yeah? So delta v over delta t is going to give me the slope a. Yeah? If I now plot an acceleration time graph, so I have acceleration on the y-axis, time on the x-axis, right? For all time, all this time, I have the same acceleration, the value of the slope. It does not change. So let's say its value was here, maybe 10 units or something, 10 meters per second squared. I find the value, and then it never changes with time. So I have a slope of 0 now. For acceleration, that means my acceleration is uniform or constant. The acceleration is not changing. That means the velocity is increasing at a regular rate. Yeah? So it's important to be able to understand this equation and each of these graphs and the connection between them. How the slope of this graph at every point essentially generates this graph. How the slope from this graph generates this graph. Yeah? If this was a curve and not a straight line, we would have exactly the same relationship between this acceleration and velocity as we have over here. Yeah? It so happens that we get a straight line here for this particular position time graph. Hence, our acceleration is constant. But we'll find that we are interested and are more capable of describing motion where that acceleration is constant and uniform. It's much harder to describe motion where the acceleration is not uniform. So we will stick with this condition where the acceleration is uniform or constant. Okay? So it's the same middle graph, a velocity time graph. And we're just going to show you the relationship between this and v equals v0 plus at, which was the kinematic equation. So at time t equals 0, let's say we're here at the origin, my velocity must be 0, v0. Yeah? So that's this value here. It doesn't have to be 0, just has to be this value v0. Could be some positive or negative value. But it's the intercept on the y-axis, v0. And at some final time, let's say here, the velocity has increased by this much, right? And that is nothing but the slope times the time. Yeah, so at. So now you see that this velocity here, which is v, this v, is the sum of v0 plus at, which was exactly our equation, v equals v0 plus at. So now you see it graphically. If anything here is unclear, please go to the discussion board for chapter 2 and let's discuss it, okay? So we're not going to derive all the possible equations that we get for one-dimensional motion, but we're going to take them as a given. We saw this first one already, v equals v0 plus at. The next one is just by the definition of velocity. So remember, this is now just the magnitude of the velocity and the magnitude of the displacement. So delta x equals the velocity times time, okay? And this is the average velocity, not the instantaneous. So average velocity can be taken as an average of two different velocities, some at time vf, okay? And that's the corresponding time. So this is the average of these two. We tend to use this equation a little less. The next equation that we use is another expression for delta x. Delta x equals v0t, so the initial velocity times time, plus half at squared. Okay, so that's the second equation. This is the first one, first, second. And then we have a third equation, v squared equals v0 squared plus 2a delta x. So we did not derive these two equations here. You will simply be expected to use these equations, okay? Note that in all of these, the condition is that A is a constant number. So the acceleration has to be uniform or constant. It cannot be changing. So whenever you want to use these kinematic equations, you need to check that the acceleration is uniform, which could be uniformly 0, or it could be uniformly some positive value, or it could be uniformly some negative value. It just needs to be uniform, okay, throughout the motion that you are considering. Okay, next we come to group work, and I want you to look at the next video where I show you how to solve this first part, and I go through this group work, okay? And we'll come back after that. Thank you.